Hey, stats friends. So, if everything is going to plan, that means we are on our last lesson for our first semester. So, this is the last section in our probability chapter. We're going to discuss conditional probability and independence, among some other topics in there too. And, full disclosure, this is one of my favorite lessons. So, take that for what you will. So, conditional probability. The probability we assign to an event can change if we know that there's some other event that has occurred. This idea is key to many applications of probability. So, very rarely in real life is probability as simple as we want to make it in our math books. So, the probability that one event happens given that another event is known to have happened is called conditional probability. The conditional probability that event B happens, given that A has already happened, is denoted as that. So we read that as the probability of B given A. So when you see that vertical line, that means the word given. Oh, haha. Be patient, Abruzzo. There's a bubble coming up. All right, so let's look at an example here. Oh, a very uplifting example involving something you may have heard of before, the Titanic. So in 1912, the luxury liner Titanic, on its first voyage across the Atlantic, struck an iceberg and sank. I'm sorry, this is not funny. I don't know why I'm giggling. That's terribly inappropriate. Some passengers got off the ship in lifeboats, but many did die. Suppose we randomly select one of the adult passengers from the Titanic. Define events F. I'm laughing at my inability to read, is what I'm laughing at. So events F. First class passengers, S is survived, and T is third class passenger. So the first question that they propose to us is find the probability that someone is in third class given that they survived. Interpret the value in context. So before we look at the math, we got to think about what we know about the Titanic. And I'm going to be honest, most of what I know about the Titanic, I know because of the movie. Yes, the movie. So third class passengers were not really given a lot of opportunity to get on the lifeboats. So I would imagine not so many survived. So what we're doing here is, as far as the math goes, when they give a condition on your probability, so here the condition is that they survived. What we do is we focus on just that portion of the 2A table. So for me in class, I literally would highlight the survived data. So that's the only place I'm going to look. Now within that survived data, they want to know the probability that someone is from the third class. So they have 151 third class passengers out of the total 442 that survived. So the key thing to take away here for conditional probability is that your denominator, your total, is only based on that condition that was applied to your probability. So this highlighting really does come in handy. Of course, they want to convert it to a decimal or a percent, so it means a little more to us, but 0.342. So the context for that is that given that a randomly chosen person survived, there was a 34.2% chance that he or she was from third class. Now that's, if I can take my emotions out of it when I stop thinking about that tearjerker movie, um, that's a higher percentage than I thought. Because, I'm thinking, all right, that's, uh, okay, proportionally, no, never mind. I was going to say that felt like a lot of people based on what I know from my very real life movie I watched. But now I realize that there was 627 third class passengers, so never mind. I'll just be quiet. All right, part B. Given that the chosen person is not a first class passenger, what is the probability that she or he survived? So the given portion represents our total for this particular problem. So given that they are not a first class passenger, so we're supposed to focus on everybody who's not a first class passenger, meaning the second and third class passengers. So as far as a denominator goes, we would have to total this 261 and 627 for our denominator. Now for the numerator, the probability component of it was that they survived. So out of just this data, the 94 and 151 survived. So we do have to do a wee bit of adding. And when we calculate that probability and change it to a decimal, it's 0.276, so 27.6%. So once again, that doesn't mean a lot to people. We got to kind of translate that for humans. It says write your answer as a probability statement. Oh, never mind. They don't want a human answer. They want a crazy math answer. So, um, oops, right here. That's the crazy probability statement. So the probability that they survived, given that they were not in the first class. So remember, this little c represents the complement. So the complement of first class would be not in first class. That was fancy. Also a very sad problem. I'm so sorry for my inappropriate giggling. All right, now this formula is probably the bane of my existence as a math teacher because as a math student, I remember certain professors of mine insisting that we use this formula, and then eventually I just realized like this formula is terrible. Um, I'm going to show it to you because once in a while we get questions that don't have any context, so this formula does come in handy. But generally, when we have those two-way tables, I don't even touch this formula. So the conditional probability formula, and notice A given B, if we were to reverse this and do B given A, we'd have a different formula. But for A given B, what you do is you take the probability of A and B occurring together, and you divide it by the probability of B, so the given. And I know what you're thinking. You're like, yeah, that seems super easy to understand, Mrs. Abruzzo. It's okay. The choice of which event is A and which is B is arbitrary. So what they're saying is it doesn't really matter how you do A given B, B given A, but the formula changes. So we got to be a little careful about this. If it's B given A, then it becomes probability of B and A together divided by the probability of A. So the idea is whoever is the given component, that's always your denominator. That's how I remember that. All right. Oh, that's cute. A survey of all residents in a large apartment. Oh, we've seen this problem before, right? It's the I think we've determined the elderly apartment complex because nobody uses Facebook if you're young, I've heard. All right, 68% use Facebook, 28% use Instagram, and 25% use both. So suppose we select a random resident at random. Given that the person uses Facebook, what's the probability that he or she uses Instagram? So that given that the person uses Facebook, that's telling me all about my denominator, right? So my denominator is that they use Facebook and they have this percentage, which we're going to write as 0.68 because the probability that they use Facebook is given to me as 0.68. That's the denominator. What's the probability that he or she uses Instagram? Now, remember, the Instagram, this we showed this as a Venn diagram on a previous question, like in last unit, or actually the last lesson. So the 25% is that middle of the Venn diagram. So someone who we know uses Facebook, how many of them also use Instagram would have to be from that center piece of the Venn diagram. So that's where the 0.25 is coming from. So if we were to calculate that, we'd get 0.368. So this is one of those cases where because of how the information was presented to me, I really did have to use that god-awful formula that I just don't like. But I'll be honest, I still muscle through it and I think about the context of it. This is a tricky question for kids because, when it's in a two-way table, it's kind of beautiful and awesome. Um, this one would be hard to create a two-way table, but we saw in the last lesson that we showed it as a Venn diagram, and that kind of made more sense to more people. So I think it would be nice to show as a Venn diagram. Oh my goodness, they just love this question. It's back, the snowmobile question. So people who are in the environmental club versus snowmobile experience. So we know that there's a total of 1,526 for this whole survey. They asked each person whether they were in the club and whether they rented, owned, or had a snowmobile, or never used a snowmobile. Sorry. Respondents were also asked whether they belonged to the. Okay, I said that. So here's our two-way table data. We've seen it like 3, 4 times by now, 5, 6, I don't know. So the first question, and this is a check your understanding. So in a moment, you're going to want to pause the video and jot down your thoughts, but they want to find the probability of n given e. So they defined our events up top here. So the probability that they never use a snowmobile given that they are an environmental club member, and then interpret what that means. And then the second question, given that the chosen person is not a snowmobile owner, what's the probability that he or she is an environmental club member? And then they want you to use the fancy probability statement. And then, is the chosen person more likely to not be an environmental club member if he or she has never used a snowmobile, is a snowmobile owner, or a renter? Justify your answer. So pause the video, jot down some thoughts, and in a moment we'll see the answers. So the first question was probability of n given e. So what we're going to want to do is because it says given e, meaning given their environmental club member, we would want to highlight this yes column. This is the only place we can look for data. So given this, meaning our denominator is 305, what's the probability that they never used a snowmobile? That would be the 212 of the 305. So they're, of course, going to change that to a decimal, and then a percentage makes more sense to most humans. So the context to this is, given that the respondent belongs to the environmental club, there's about a 69.5% chance that he or she never used a snowmobile. So you're really just restating the question that's written in probability notation in English. That's all you're really doing, but now you're also adding in this answer of 69.5%. All right. The second question is the reverse. They gave us the English and they want us to calculate it, but then write it as probability. So given that the person chosen is not a snowmobile owner, so here's the owners, right? So we would only be able to look at these guys, the renters and the never used. So looking at these two, remember these two would be the complement of the owners. So when we go to write this in notation, we're going to have to use that complement notation. So given that we have the complement to the owners, that's why you're going to see this right here. What's S? Oh, they used S for snowmobile owner. All right. So the complement of being an owner, that was the given part. And then I forgot the rest of the question. What's the probability that they're an environmental club member? So again, we're just looking here. So club member would be these two here. We'd have to add those up. I can do this in my math teacher. 289 over, I cannot add that up. All right, 289 over 1231, which they converted to 0.235. So in this case, 1 and 2 are just basically the opposites of each other. But you had to calculate the probability in both. So in question 3, they wanted you to compare which one was more likely. So is it more likely to not be an environmental club member if they used a snowmobile, have never used a snowmobile, if they're an owner, or if they are a renter? Now justify your answer with math. They don't want to know about your personal experience with snowmobiles, okay? This is a math question. So what they're doing is they're looking for all the probabilities of not being an environmental club member, given the different types of ownership of snowmobiles. So given that you've never ridden one, given that you're a renter, and given that you're an owner. I noticed they've changed their notation here on renter and owner. I wonder why. Oh well, whatever. So for each of these calculations, because it's like given they've never used one, you'll see the denominators are coming from this column over here. So the first one is a denominator of 657. The second one was a denominator of 574. And then the third one was a was a denominator of 295. So probability that they were a club member would be this number over this number, this number over this number, this number over this number. Now, of course, fractions mean nothing to us. So when we calculate them, we want to see the percentages or the decimals. And this one has the highest probability. So the chosen person is more likely to not be an environmental club member. Oops, did I do the wrong thing? Sure did. Abruzzo, it was not. It was this number over this number, this number over this number. Yeesh, sorry about that. All right, anywho, more likely to not be an environmental club member if he or she owns a snowmobile. Now, it is not your job to dive deep and figure out why that is. What's the psychological or environmental impact as to why that is? That's the next stage in the study. For now, we're just doing the math. All right. Let's talk about independence, because this idea comes up a lot later on in our inference chapters, where we have to show that these events are independent from one another. So A and B are independent if knowing whether or not one event has happened, that it does not change the probability that the other event will happen. So, like, logically, we know what independent means in math, but we have to show this with math, and this is something, like I said, it's going to come back. So, in other words, if A and B are independent, probability of A given B is equal to the probability of A given the complement of B, and is also equal to the probability of A. Now, for me, that's a lot to think about, and this complement thing kind of messes with my brain. So what I typically do later on in this class when we have to prove independence is I say the probability of event 1 given event 2 is equal to the probability of event 1. So which is event 1 and event 2, it doesn't matter. We'll find that out later. But as long as you can do the conditional probability and show that it equals the probability of the first event, what would have been in your numerator, if you want to think of it that way. That's a bad way of saying it. Ignore what I just said. Okay, so they want to know, this is that pierced ear question where they're comparing the males and females and whether their ears were pierced. The probability that someone has a pierced ear given that they're male could be calculated by, well, looking at the male data and saying pierced over total, so 19 over 90, which comes out to 0.211. Now, alternatively, they did the complement to that, and by that I mean the denominator, the given part. So pierced ear given that you're female, so probability of um, having a pierced ear given your female would be 84 over 88, which is 0.579. And right away, I can see that these are not equal to each other. So that tells me that these two events are not independent of one another. The other thing we could have done back at the beginning here when we did pierced ear given male, we could have just calculated the probability that someone has their ear pierced. So that, and just somebody on the table. So that would have been a 103 over a 178, which is not equal to 0.211. So it doesn't matter which pairing you come up with. You just got to show that they're not equal to say that they're not independent. Or if they are independent, that they are equal. So is there a relationship between gender and handedness? To find out, we use Census at School's random data selector to choose an SRS of 100 Australian high school students who completed a survey. The two-way table summarizes the relationship between gender and the dominant hand. Suppose we choose one student in the sample at random. Are the events male and left-handed independent? Justify your answer. So what we have to do first is calculate some sort of a conditional probability that has to do with male and left-handed. So they calculated the conditional probability that someone is left-handed given that they're male, and that came out to 0.152. And then they did the complement to that given component. So left-handed given that you're female. So that was 0.056. So with these not equaling each other, that means these are not independent events. So because these probabilities are not equal, the events male and left-handed are not independent. Knowing that a student is male increases the probability that the student is left-handed. So just they're pointing out here that when you look within the male condition, it's 15% versus female, which is like between 5 and 6%. Okay, so not independent. Again, they didn't have to do it that way, but it works. They could have said, once they calculated this first conditional one, they could have said, what's the probability that someone is left-handed? Well, that would have been the 10 over the 100, which is 0.1, which is still not equal to 0.152. All right. So this is a check your understanding for conditional probability and independence. After I read through it, I'm going to have you pause the video and jot down some thoughts. Now, first thing I noticed is they didn't total it for me. I hate when they do that, but I guess this is pretty easy to total, so I got this. We have, for each random process, determine whether the events are independent. Justify your answer. Shuffling a deck of cards and turning over the top card, putting it back into the deck, shuffling it again, and turning over the top card. They want to know if these are independent. Okay, so we'll talk about that in a moment. And they did want you to define A as the first card is a heart and the second card is a heart. So then we have shuffling a deck of cards, turning over two top cards one at a time. So first card, second card. The first card's a heart, the second card's a heart. Are those independent or not? And then they look down at this data. We got 28 students in Mr. Tabor's AP Stats class took a quiz on conditional probability and independence. By the way, Mr. Tabor is one of the authors of your textbook, and he still teaches statistics. He is wonderful. If you ever see a video on him, go ahead and watch it. He's a very talented teacher. All right, the 2A table summarizes the class's quiz results based on gender and whether a student got an A. Choose a student from the class at random. The events of interest are female and got an A. So they want to know if those are independent or not. And you're going to try to prove it with math. And that's my only hint I will leave with you before you pause the video. All right. Now, this one about the cards, they didn't take the time to show the math. They could have. You know, it's interesting. A lot of kids don't know a lot about a deck of cards. There are 13 hearts in a deck, right? 2 through ace. And remember, they're putting the card back into the deck. So the probability that it's not changing, I guess, is the difference. The second time they go to draw a card, it's not going to be affected by that first pull because they put the card back in. So event A and B and number 1 are independent because they're putting the card back. We call that with replacement in probability. Knowing what the first card was will not help us predict what the second card will be. That's kind of the key takeaway there. I really admire professional poker players because they can sit there and they calculate like the likelihood of things happening based on what they see on the table, and I think that's wild. Like I cannot even keep track of the things on my desk. Like how am I going to keep track of all the cards and all the probabilities that are associated? And they have multiple decks of cards. That's crazy. All right, so the second question, remember they turned over 2 cards. So a card and then another card on the table. So this time, the second card is either more or less likely to be a heart based on whether the first one was a heart. So this time, these events are not independent because if the first one is a heart, that means the probability of the second one being a heart is lower than it would have been. Okay? So they are not independent. We didn't do any math on 1 and 2, and that's okay. But now on number 3, we want to be able to do a little math to back it up. So the 2 events of interest, remember, were female and got an A, and they want to know if that was an independent, if those events are independent. So the first thing they calculate was once we know that a person chosen is female, so given that they're female is where they're going with this, the probability that they got an A. So they're only looking at the female data. So that's what 21 is a denominator. That they got an A was 3 out of the 21. I need to reread this apparently. Once we know that a person chosen is female, this does not help us predict that she got an A or not. Oh, okay. I guess I didn't read that very carefully. My bad. Oh, says that's because I didn't read it at all. Gosh, Abruzzo, rewind. Choose a student from the class at random. At random. All right. So overall, 4 out of 28 students got an A on the quiz. Oh, there we go. And among the females, 3 out of 21 got an A on the quiz. So if you look at those fractions, they reduce to the same ratio. So this is the overall this is so confusing about independence. So remember back a few slides where we said, okay, you can look at the conditional stuff and see if it equals each other, meaning like got an A given female, got an A given male. Well, actually they didn't look at that yet, but we could. Got an A given male would be 1 out of 7. Kablamo! It's that same magic 1 over 7. So since you can prove that the probability equals the other probability, no matter where you're looking, they're all 1 out of 7, these events are independent, which is good because if they were dependent, we would have to classify something sketchy going on in this class that just because they were female, they either did or did not get an A. That can't happen. That shouldn't happen. That riles me up a little bit. All right. Hey, you know what I forgot to do is warn you guys where we're separating things. Um, oh man, we're probably like way into day 2 by now. Let's see. I figured it out a while ago and now I can't remember. Eh, it's the last lesson, guys. Just hang with me here. Let me see how many slides I have left. Yeah, we're about halfway. I bet this is day 2. We'll go with that. All right, the general multiplication rule. About 55% of high school students participate in a school athletic team. All right, there's your stat. Here goes. 6% of these athletes will go on to play college in NCAA sport. What percent of high school students play a sport in high school and go to college, move on to college to play in the NCAA team? So there's that conjunction and that we've discovered pops up in math and it means something. So 6% of the 55%. In math, generally, the word and, we need to multiply these things together. So 6% times 0.55 or 0.06 times 0.55 is about 0.033, which is 3.3%. Okay, so what they did there is they multiplied them together. Now, look what happened here. They multiplied the probability of them playing a high school sport by the probability that they are going on to the NCAA team given that they were in a high school sport. Okay? That's what allowed them to multiply those together. For any chance process, the probability that events A and B both occur can be found using the general multiplication rule. So, the probability of A and B occurring, which we know is an intersection, is probability of A times the probability of B given that A occurred. Now, this gets a little confusing because sometimes these are independent events. So B given A occurred doesn't really matter. Like sometimes kids get hung up at this part because they're like, I don't see any conditions. There's not always a condition if we'll see later on if the events are independent. So the general multiplication rule again, we're going to have it's that social media question. Oh, it's a different one. Thank goodness. All right. The Pew Internet and American Life Project reported that 79% of teenagers from 13 to 17 use social media. That can't be right. It's got to be higher than that. And that 39% of teens who use social media feel pressure to post content that will be popular and get lots of comments or likes. Find the probability that a randomly selected teen uses social media and feels pressure to post something that will get lots of likes. So here we have that and word again. So we know we're going to multiply them together. And the second probability is 39%. Those are all the teens who do use social media and feel pressure. So all we got to do is multiply those together. 0.79 times 0.39, roughly 30.8%. All right, tree diagrams. Really great visuals. You know me, I love a visual. And it helps you kind of follow the logic of the situation, I think is what's helpful about a tree diagram. It shows the entire sample space of the chance process involving multiple stages. So what happens if this, and this happen? And if there's multiple stages, there's multiple branches, to use a word from the tree diagram. There's multiple branches in which you can kind of offshoot. So we got to be careful. Oh man, I just really nerded out in my head. I was like, oh, this is just like the multiverse. I just got done watching the Loki show and I was like, oh man, all the timeline branches. All right, all my nerds out there, you know what I'm talking about. The probability of each outcome is shown on the corresponding branch of the tree. All probabilities after the first stage are conditional probabilities. So that's what's nice about a tree diagram is if you just keep following the branch out to the right, it's all assuming that the previous branch occurred. So those are the conditions that are already done. Oh, this is a cute one. It displays a sample space of randomly choosing a school day and noting if Shannon hits the snooze button or not, and whether she gets to her first class on time. So, little Shannon is more likely to hit the snooze button than not. So, 60% probability of hitting the snooze button, 40% probability of not. Now, if she were to hit the snooze button, she is on time 70% of the time, and therefore not on time 30% of the time. But if she doesn't hit the snooze button, she is on time 90% of the time, and she's late 10% of the time. Well, you know what, Shannon? I feel like you have some concrete data here to tell you to not hit the snooze button, but whatever, girl. Oh, they didn't want us to do anything there. They're just showing. So they could ask us questions like, what's the probability that Shannon hits the snooze button and is on time? Well, we would multiply her branches together as we follow it along. So hits the snooze button, is on time. We would multiply zero point 0.6 by times zero point 0.7, and we get 0.42 on any randomly selected school day. All right, Harris Interactive reported that 20% of millennials, 25% of Gen Xers, and 21% of baby boomers, and 17% of matures, that's a nice way of saying it, read more ebooks than print books. Really? I would have thought millennials was higher. I'm kind of on a borderline millennial age. I'm not really sure what I am anymore. All right, anywho. According to the U.S. Census Bureau, 34% of those 18 and over are millennials, 22% are Gen Xers, 30% are baby boomers, and 14% are matures, if you will. Suppose we select one U.S. adult at random and record which generation the person is from and whether she or he reads more ebooks or print books. Draw the tree diagram. So notice the order in which they stated that. We select the person, we figure out what generation they're in first. So that's going to be the first branch. So are they a millennial, a Gen Xer, a baby boomer, or a mature? And they put their probabilities right there on the branch itself. That helps. Now, once you get to the whatever age stage they're in, whether they read an ebook or not was given to you, right? So the millennials was 20% reads more ebooks, which means the complement to that 80% would be they read more print books. So they gave you all of the top branch here, and you have to use the complement rule to find the bottom part. So 21, 79, 17, and 83. So there's your tree diagram. I don't know. Is it easy for you guys to read? I hope. I think it does display the situations nicely. And then it allows us to actually find probabilities. So find the probability that a person reads more ebooks than print books. So there's going to be a lot of colors coming up here. Hang tight. The probability that a person reads more ebooks. That would be for the millennial crew, for the Gen Xers, for the baby boomers, and for the matures. And we're going to have to add all those probabilities together. But remember, for the millennials, you got to multiply these two pieces together. And for I feel like something's not lined up here, right? Eh. Okay, anyways, Gen Xers, there we go. And then we got the baby boomers. There we go. And the matures. There we go. Oh, I know what happened. They made it seem like this was a fraction right here. I was like, this isn't right. They literally just want you to add these four things together. Type it all in your calculator, I guess. They seem to have simplified this red and green box right here. Okay, thank you for the color coding, guys. That was hard for me to follow. And then they simplified this purple and blue box here. And when they add these two fractions, no, Abruzzo. This is not a fraction at all. Gosh, I think something's really weird on my formatting here, guys. I'm just going to quickly hand calculate something on my own little calculator. Bear with me. I'm going to pause the video. Yeah, I think I need to fix this diagram. This image is really hard to read. It's just green plus purple plus red plus blue. That's all we're supposed to be doing here. That's how they got the 0.2098. I was wondering, like, why are these fractions? They aren't. I have a really bad image. I need to fix that. Sorry for the confusion. That was supposed to be a pretty easy question. I made it hard. All right, same tree diagram. Suppose the person chosen reads more ebooks than print books. What's the probability that he or she is a millennial? Now, remember, we just calculated the probability that they read more ebooks, didn't we? We just found that to be the 0.2098. So the probability that he or she is a millennial, remember, we can find this out by saying the probability of millennial and reads ebooks. Okay, so millennial and ebooks would be the 0.34 times the 0.2. And then divide that by the probability that they read more ebooks, given that they read more ebooks. Well, we already found that. So the 0.2098. So that came out to 0.3241 for the calculation. Again, The calculator button pushing is not really what they're interested in here. It's, can you interpret? Can you figure it out? Trying to see if there's a better way for us to explain that question. I think that's okay. I really, at the heart of this, I just hate that given conditional formula, and I'm always looking for a way to get around it. But I think in this particular example with the tree diagram, that probably is the best way. So, sorry. Had that data been in a two-way table, which for me, if the data wasn't a tree diagram and I wasn't forced to make it into one, I probably would have done a two-way table. It would have been pretty nice, I think, to figure out. All right, so here's to check your understanding. Computer company makes desktops, laptops, little tablets in two states, California and Texas. California factory produces yada yada. All right, there's a bunch of data here. Oh my goodness. I think this stuff has to be put into some sort of a diagram. Oh, and what do you know? Question 1, construct a tree diagram and model this random process. So when you construct your tree diagram in a moment, suppose we select a computer at random from the distribution center and observe where it was made and whether it was what type. Your tree diagram is going to start with where it was made and then branch off into what type of device. So in a moment, you'll be doing that. And then you're going to find the probability that the computer is a tablet. And then you're going to do a conditional probability where given that the tablet computer is selected, so use that number 2 answer, what's the probability that it was made in California? All right, please pause the video and jot down some thoughts. My suggestion is obviously to start with your tree diagram because that's question number 1. All right, so here's your tree diagram. We got California and Texas. And then all the data from the problem was California's desktops, laptops, tablets, and Texas desktop, laptop, tablet. So now that we have the tree diagram, it'll be pretty easy to answer the next question, which was find the probability that the computer is a tablet. So we have to go and find all the tablet probabilities and add them together. So following the tree out, the branches out, so 0.4 times 0.45 plus 0.6 times 0.7, and we'd add those numbers together, and we get 0.6. So the context there, the probability of selecting a tablet is 60%. So the final question was find the probability that your device was made in California given that it's a tablet. So remember the given formula says that you can use that tablet probability in the denominator, the one you just found, and then up in the numerator, probability that your device is made in California and is a tablet. So on your tree, California tablet right here, 0.4 times 0.45 is where they got this 0.18 from. And then they divided those and they got 0.3. So given that the tablet was selected, there is a 30% probability that it was made in California. Okay. So when A and B are independent, that means the probability of B given A is equal to probability of B. I kind of talked about this earlier, where the multiplication rule confuses kids sometimes because they're like always looking for conditions, and there's not always conditions. Like if they're independent, then you don't have to worry about it. So that's wonderful. We can simplify the general multiplication rule to just say probability of A times probability of B in those cases. So yay for independence. If they are independent, then you just multiply them together. Easy as that. It only works that nicely though if they are independent. So you will see us checking for independence sometimes. Sometimes independence is obvious, like those deck of cards questions, like you put pull a card and you put it back in the deck. Well, the next pull is going to be independent from the first pull. But if you keep that card out, all of a sudden you're not independent anymore. All right. Oh, man, my brain's going tired. Many people who visit clinics to be tested for HIV, the virus that causes AIDS, don't come back to learn their test results because they're scared, I would imagine. Clinics now use rapid HIV tests that give a result while the client waits. In a clinic in Malawi, for example, the use of rapid tests increased the percentage of clients who learn their test results from 69 to over 99%. The trade-off for fast results is that rapid tests are less accurate and slower than laboratory tests. Applied to people who have no HIV antibodies, one rapid test has a probability of about 0.004 of getting a false positive. So saying that someone is HIV positive even though they're not. If a clinic tests 200 randomly selected people who are free of HIV antibodies, what's the probability that at least one false positive will occur? Assume that the test results for different individuals are independent. Okay. So let's start with the probability of no false positives. So meaning all 200 tests come out negative, because the premise of this problem is that every one of these people is supposed to come out negative. So 0.996, if you can think about where they came up with that number, that would be the complement to this false positive number. So 1 minus 0.004 is 0.996. In other words, the test is 99.6% accurate. So 2 tests, boom, boom, multiplied together, 3 tests, 4 tests, 5 tests, all the way out to 200 tests. So a simpler way of saying that in our calculator is 0.996 multiplied together 200 times, so to the 200th power. So that is a 0.4486, so 44.86% probability that all the tests come out with the appropriate answer. Now, the complement to that would mean that there is some false positives happening, at least one. So there's a 55.14% chance that there's a false positive. So as a, medical researcher, you have to stop and think about like the drawbacks and the benefits to testing this way. If over 99% of the people are staying to get their result, even if their result is a false positive, at least then that would stop the person from like continuing on in their life without actually knowing what's going on. Now, I'm sure that if they use these rapid tests and someone comes out with a positive, then their next step is to say, okay, you're going to go do the more thorough laboratory test that is going to take a little longer. But at least the person is kind of flagged and signaled like, hey, you may have the HIV, virus that causes AIDS. So I'm sure they have protocol for that, and I know that that is a serious topic. So I'm glad they're doing a lot of research on that. All right, checking our understanding. Questions 1 and 2 refer to this setting. The New Jersey Transit claims that its 8 a.m. train from Princeton to New York has a probability of 0.9 of arriving on time. Assume that's true. Find the probability that the train arrives late on Monday, but on time on Tuesday. So you're going to multiply 2 events together on that one. Okay, figure those out. And then what's the probability that the train arrives late at least once a day? At least once in a 5-day week. And then the government data show that 8% of adults are full-time college students and that 15% of adults are 65 or older. If we randomly select the adult, what's the probability that they are a full-time college student and 65 or older? Is it equal to 0.08 times 0.15? Why or why not? So pause, try to write down some thoughts, and we'll give you the answers here next. So first question about the train arriving late Monday but on time Tuesday. So the probability that the train will be late is 10%, right? If it's 90% going to arrive on time, that means the complement is 10%. So Monday late, Tuesday on time multiplies together to be 0.09, so 9%. That's all they wanted from you on number 1. All right, so number 2, they're going to do that cutesy complement thing, right? So they want to know the probability that they arrive late at least 1 day a week. Well, if you can figure out the probability of it never arriving late at all, and then you can do the complement to that, that'll be our answer. So arriving on time 5 days in a row would be 0.9 times 0.9 times 0.9 times 0.9 times 0.9. That's where this 90 to the 5th power is coming from. And then 1 minus that 0.9 to the 5th power, that's how they calculated the 0.41. So 41% chance that the train arrives late at least once in the week. Now later on, when we talk about more probability formulas, you'll see some other fun stuff we're going to be working with. So hang tight for that lesson. All right. probability of full-time college student and age 65 or older. So they're claiming that that was not true, to say it's just simply 0.08 times 0.15. Let me go back to that question real quick. So the 0.08 is that full-time college students, and then the 0.15 is that those 15% of adults that are 65 or older. So the question here is, were we allowed to just multiply those together? And the answer is no, because they are not independent, right? You can be an adult 65 or older and a college student, and it doesn't tell you whether or not they are. So knowing that a person is a full-time college student is going to decrease the likelihood that they are an adult, age 65 or older. So they're not independent events, which is why we couldn't just simply multiply their straight probabilities together. In order to calculate that event, we would have to know the conditional probability of the full-time college student given that they're, well, one or the other, either a full-time college student given that they're 65 or older or a reverse of that, which we don't know. Oh my goodness, that's the end of the lesson. That's sad because that means it's the end of the chapter. I feel like there is definitely more probability we're going to be talking about shortly. But as far as the official chapter goes, that's it. We are going to do so many problems together. And I think what happens in the probability chapter is we just throw a lot at you and you're like, what? There's no magic bullet to probability. There's a lot of common themes, you might have sensed a lot of multiplication going on in your life, but then there's these weird things like, are they independent? Are they not? Am I allowed to multiply them? Um, I think it just comes with practice. And that's why when we learn probability, we usually do it this way. We just like dump a bunch of information at you, and then we just look at example after example after example, and we really just try to expose you to them. So this is undeniably one of the harder chapters of our class. Um, Regardless of how your teacher feels about it, it is a hard chapter. So don't fret if you're like, wow, I just don't get it yet. We haven't had that practice yet. This is one of those things in stats class where we just have to practice it to death. And we're going to keep throwing it at you now until the AP exam, okay? If, like I said, if everything's going right, we're probably around December right now. Guys, we got months. We got months to throw probability at you. Don't you worry. Obviously, it's a big topic in our course. And if you ever do end up taking another stats course in your future, if it has the word probability in the title, then you'll probably be excited to have this chapter in your tool belt. All right, good luck, everybody.